thank you for the invitation and for the possibility to speak here. So I will be talking about family of models which is called free fermions in disguise. And this is my favorite topic now, and I want to tell it to you to draw attention to this family of models. Maybe I really hope that some other people will start to think about it. So this is a new business where we can compute exact results for a family of models. And really strangely, there is very little interaction between traditional methods of integrability and these new results. So that's why I think it's really interesting. Maybe some connections will be found later, and which might lead to better understanding. It's new, we don't know yet. And it's really strange. So last time I was walking in our department on the floor, and then I met somebody, an older professor, and he asked me, what are you working on nowadays? And I said, free fermions. And then he laughed and said, come on, free fermions? I mean, is there anything that can be done about free fermions? And then I said, yes. That is a new family of models which are surprisingly free fermionic, even though they don't look like it. So that's the point. The free fermions are hidden in these families of models. And this is a new business, meaning that it was started in 2019 by Paul Fendley. No. So he published the first model, but it's actually a family of models, which means that different types of Hamiltonians can be added, and they can be free fermionic. And they exist mostly in one dimension, but there are even some really strange examples in 2 dimensions, and even higher dimensional can be found. They are really exotic models, but not restricted to 1D. That's my first message. Nevertheless, in all of this talk today, I will discuss one-dimensional models, so spin chains actually. And actually, also the model of Paul Fendley was a one-dimensional spin chain. I will write down the Hamiltonian, what was in his paper. So the Hamiltonian is a summation over sites J. It will be a spin chain model with open boundary conditions. There will be some coupling constants Bj, this is a real number, and then Pauli matrices. I can write it, no actually, where is the sponge? Yeah. No, that's okay. A better convention is when I write Z and X. So this X on site J, this X on site J plus 1, and this on J plus 2, and these are Pauli matrices. So you see that this is a Hamiltonian which has local interactions, because Hamiltonian density acts on 3 neighboring sites. Nevertheless, it's different from what we know earlier. It's a new model. And then Paul Fendley published this model in a paper in 2019, and he showed that even though this model looks like really strange, it has no U1 symmetry, there is no connection to anything what we know earlier. It has free fermions, and it can be diagonalized by free fermions. There exist free fermionic creation annihilation operators, and this will give you actually the spectrum of this model. So this was his result. And then later, I also joined in a little bit later. So right now I have 3 papers on this topic. In one paper, actually with Paul, we found an extension of this family, where we add some more terms to this Hamiltonian so that it keeps being free fermionic. And another paper, I also considered quantum circuits with these free fermionic models. And then in the last paper, what we published maybe 1 month ago, it was done by 2 postdocs in my group in Budapest. We computed exact real-time dynamics for the first time with this family of models. So there were some couple of works previously, also by other people, Stephen Flamia, Adrian Chapman, and some collaborators from the United States, who also contributed to this theory. I will explain maybe a little bit later how. But all works previously, they always constructed only the spectrum. So they showed how to diagonalize the Hamiltonian, how to compute eigenvalues. And for the first time, what we published 1 month ago, we solved the so-called inverse problem, or at least partially we solved the inverse problem, and we could compute correlation functions of local operators specifically in this model. And this was our result, what we put online, and this is what I will introduce a little bit in this talk. I will not give too many technical details, and please feel free to interrupt me also during the talk. It's perfectly fine. So before we go to the so-called disguised free fermions, let me just very briefly recap how does it look like when we have free fermions in a normal, well-known way. So when we have the normal free fermions, maybe it's easier to think about real free fermions, so Majorana fermions. Let's say that in a certain spin chain, we have so-called Majorana operators, key of with an index k. These are operators that act on some Hilbert space, and they have, if they are Majorana fermions, then they have some exchange relations, some properties. So they are real. If they are real free fermions, then some properties are that it should be operators should be Hermitian. Actually, if they are free fermionic, then they should square to 1, Majorana fermions, and they should satisfy the anti-commutation relation that key k anti-commuting with key L is 2 times Kronecker delta KL. So these are defining relations for Majorana fermions. There are two types of questions. First question is, how can we construct Majorana fermions on a spin chain? Second question is, what type of interesting Hamiltonians can exist which are solved by Majorana fermions? So these are two questions. So the first question is, how can we construct Majorana fermions on a spin chain? Is the so-called Jordan-Wigner transformation. So this is well known. I will not write down the formulas. I'm sure most of you know. There is a well-defined way going back to the early days of quantum mechanics by Jordan and Wigner, who found out how to construct these operators using the Pauli matrices. The key idea is just to insert the so-called Jordan-Wigner string, which will give you the signs necessary to have this fermionic anti-commutation relation. So if you have your Majoranas, then you can construct Hamiltonians, which can be solved by these Majorana fermions. And the general formula is the following. You would want a Hamiltonian which is quadratic in the Majorana fermions. So the most general Hamiltonian which is solved by Majoranas looks like this, that I have a summation over indices j and k. I have some coefficient matrix here. These are actually purely imaginary numbers in the normalization that I will use. And I have this bilinear product of Majorana fermions here. I mean, they anti-commute, so we can choose this to be antisymmetric matrix, and it's with purely imaginary coefficients, but that's not important. And then using these anti-commutation relations, we know that if we have a bilinear Hamiltonian, then we can solve it, meaning we can construct fermionic creation annihilation operators, and we can compute the spectrum. And then the spectrum will come actually out of the eigenvalues of this matrix. And what is good? It is good that the size of this matrix scales only linearly with the size of your spin chain. So the Hilbert space grows exponentially, but if we want to find eigenvalues of a generic Hamiltonian like this, we don't need to diagonalize exponentially big matrices. We only need to diagonalize this matrix, which grows linearly with the length of the spin chain. Actually, typically if we have length of the spin chain L, then this matrix will be 2L times 2L. The size, which is really nice. It's a big help. And that's why free fermions are good. Because even if it is inhomogeneous, so even if the numbers here are arbitrary, it is still a small matrix that we need to diagonalize. Now this is one thing. I want to add a comment here. My comment is that it is not only the Jordan-Wigner transformation which can give us Majorana fermions. There are obviously other choices. So this is an abstract algebra, and this algebra has, of course, many representations in a spin chain Hilbert space. You can start with your Jordan-Wigner representation and then transform it away if you want, and it's a different Majorana fermions. And then you can get different Hamiltonians. So the family of models allowed by this part is actually really large. And just recently, in 2020, if I remember correctly, there were 2 independent papers which not categorized, how to say, they gave conditions for this construction to be possible. I will explain what they did. The 2 papers were actually only 1 or 2 months apart from each other. One was by the Japanese group, and the other one was from a group in the United States. I will not cite now archive numbers. If somebody is interested, I can look it up and show you in the break. But let me explain what was in these papers. So they asked the following question. If I start with a Hamiltonian like this, that here I add some kind of numbers, let's say alpha j, these are real numbers, and there are some operators h, j. These operators are Pauli strings, which means that every operator is a product of only Pauli matrices, not sums of Pauli matrices, etc. Then the question is there any way to find Majorana fermions such that every Hj will be somehow a bilinear of this type? I mean, we should use different indices, so this J is not the same as Js here, is different indices, sorry. So this is a question. If I give you a Hamiltonian, can you know that there exists maybe some kind of Majorana fermions which give you a bilinear expression for each Hj? Maybe if it exists, maybe the Majorana fermions are actually different from the Jordan-Wigner. Maybe it's a different Majorana representation. Nevertheless, if you find this correspondence, then this can be diagonalized. And this question was completely solved by these two papers that I did not write the archive number. And they gave a graph theoretical criterion, which is a sufficient and necessary criterion for this construction to work. So this is completely settled. And I will not give you this graph theoretical condition now. It's not the main topic now. It can be found. My message is that this is solved. And I just want to tell you that in my view, it is really strange that after almost 100 years, it took us to 2020 that this problem was solved. Maybe people didn't look at it. I don't know. But it is really surprising that it was only solved so recently. I can give you one more point why this result is important. Because if you take your Majorana fermions, let's say the normal Jordan-Wigner fermions, it might be that you have a Hamiltonian which has order 4 terms in your chosen Majorana fermions. But maybe there is a different type of Majorana fermions, some kind of key J tilde, different representation of the same algebra. And then in the new operators, maybe your Hamiltonian will be actually bilinear. So that's why it's important to have this kind of classification. That's why it's a really important result. It's a graph theoretical condition. Anyway, I will not go into that. We can talk about it in a break if somebody is interested. So this is what I would call Jordan-Wigner and generalized Jordan-Wigner. It is generalized Jordan-Wigner because I allow for any kind of Majorana fermions, not just the normal Jordan-Wigner fermions. And now we go one more step. So now we go to a family of models where we know that the Hamiltonian is free fermionic, but this construction will not work. Which means that using these necessary and sufficient conditions, you can prove that in your model there will not exist Majorana fermions such that the Hamiltonian is bilinear in your fermions. So it's a theorem, and this theorem is actually holds for this Hamiltonian. We know that this Hamiltonian is free fermionic, and we also know that this construction does not apply. So this is the strange and new thing. Which means that here we will have free fermions, and they are disguised, which means that the construction is more complicated than what is written here. And I will explain what it is roughly, even though I will not have time to go into all the different details. So I will erase this. This was an important starting point. And now we go beyond this. So if we don't have the Majorana fermions, then you would ask, okay, but then what are the fermions in this model? So the statement that was proven by Paul Fendley is the following. If you take this Hamiltonian, then there exist free fermionic operators psi of, let's say, k, and psi dagger of k, which I can also call psi minus k and then k bigger than 0. That's just a choice. That satisfy free fermionic commutation anti-commutation relations. These are the usual ones. So it will be simply the following, that psi k anti-commutes with psi l, and this goes to, there is a normalization factor, but it can be transformed away. So eventually it will be, how is it, minus L. So all operators anticommute with each other except for if an operator anticommutes with its adjoint. And these are fermionic creation annihilation, these are the anti-commutation relations of creation annihilation operators, what we know. And then the further statement is that the same Hamiltonian can be diagonalized, which means that there will be a summation here, k going from 1 to s. There will be some one particle energy is epsilon of k, and here is a operator which is basically occupation number operator, but in a special choice. I choose it like this, that psi k commutator with psi minus k, or psi k dagger. This operator, written in this form with this normalization, has eigenvalues plus or minus 1, so it acts similarly as Pauli matrix Z if you want. And then every term gives you an eigenvalue plus epsilon k or minus epsilon k, which are single particle energies. So the statement is that this diagonalization is possible where these operators satisfy this algebra, which means that you can use these ladder operators to create and annihilate fermions. This was the statement of Paul. But of course, I need to tell you what are these free fermionic operators, how they emerge, and what can we compute with them. But before we go there, I want to tell you a certain detail which is really surprising. That here, it was really implicit, I didn't write too many details, but the summation goes, let's say, from 1 to L. And then here the summation goes from 1 to S. And roughly the statement is that the number of fermionic eigenmodes is roughly L over 3, which is really surprising if you think about it. So this means that in this model, the number of fermions is actually less than what is given by the Hilbert space dimension, which also tells you that every eigenstate will be exponentially degenerate. This is the statement. So in a normal model, if you have a volume L, then the number of fermionic eigenmodes will be also L. So you will have L different one-particle energies. Here in this model, you only have L over 3 different one-particle energies. So every eigen level will be exponentially degenerate with the same degeneracy. And the reason for this degeneracy is actually non-abelian symmetry algebra which exists in this model. Actually, it is not known at present what is this non-abelian symmetry algebra. So Paul Fendley could manage to write down some generators and some commutation relations, but the full algebra is not known. So this is an open problem to anyone who is interested. What is the algebra here in this model which gives us this really giant exponential degeneracy? We don't know. Okay? A further comment before we move on. I didn't really stress it, but there are these real numbers here, and they are arbitrary. So the model is free fermionic, even if I don't take homogeneous case. But this is true, if you think about it, this is true also for earlier free fermionic models. So if you take XX model, XY model, if it is free fermionic in a homogeneous case, then you can also add inhomogeneities, or what's that called, disorder. It is also free fermionic, if you think about it. The same thing holds true here, so it is wider than integrability. You know, for integrability we need homogeneous couplings always, or maybe some steps 2 staggering or something like this, but here it can be arbitrary. And of course these real numbers, they will change what are the fermionic creation annihilation operators, but that's okay. Okay, so these are some strange properties of the models, and then let's go to a little bit to the fermionic operators themselves. Okay, so if they are not coming from Majorana fermions, then what are they? How can we create them? And what can we compute with them? So first thing is that in these models, there also exists a transfer matrix. So a transfer matrix with a spectral parameter U, and it is normalized in the way that at 0, this is the identity operator. And then in the usual way, this transfer matrix will generate us commuting set of charges. So the transfer matrix is constructed in a similar way as in integrable models, but actually there are 3 different Diepol's definitions for this transfer matrix. And one definition is what people working with beta ansatz would actually know. So there is a certain type of double row monodromy matrix definition for the transfer matrix. If you know boundary integrability, you can understand one definition of the transfer matrix is you take something like this, that you have a spin chain. These are your spin chain lines of 1/2, and then something like this is happening. It's very roughly the idea for those of you who have seen something like this. It's a little bit different because it's a 3-side interacting, but some generalization of this idea is happening if you saw these pictures in boundary algebraic beta ansatz. So that part is understandable. And log of the transfer matrix generates us higher conserved charges. So just like usually, TU commutes with TV for arbitrary spectral parameters. And there is an inversion relation for the transfer matrix, which can be proven. So it turns out that T of U times T of minus U is actually identity matrix multiplied by a polynomial, which depends then on U square. You can compute this polynomial. I don't have time to go into the details, but there is a good definition of this polynomial using simply the Hamiltonian, and there is a recursive definition using these BJ parameters. So very efficiently you can compute this polynomial. It is of order S in U square. Remember that this S was roughly L over 3, which means it's lower order. And then it turns out, this is what Paul Fendley found and actually proven, that if you look at those points where the transfer matrix is not invertible, so you look at the certain points where P of U squared is actually 0, then these will be some values indexed by L, where L goes from 1 to S. It turns out that the one particle energies, which appear here, will be just given by the inverse of these zeros. So this is a strange result. I don't know if it's strange or not, but the one particle energies will be just given by 1 over UL, where UL is a root of this polynomial, where the inversion cannot, where the transfer matrix cannot be inverted. So that's one statement. It's a central statement which was found by Paul. And the next statement is I don't know if it's surprising or not. Maybe you can tell me. Next statement is that the free fermionic operators, psi of L, will be proportional to the following expression. You take a root of this polynomial, and then you take a combination T of UL, certain edge operator, I will explain what it is, and T of minus UL. So what is this edge operator? It's a specific operator on the spin chain, what depends on a certain choice. It does not matter so much. The edge operator is such that it commutes with every term in the Hamiltonian except for the first term, with which it anti-commutes. So in our case, I mean, there are different types of choices. In our case, we could, for example, choose that the edge operator is X operator, Pauli X acting on site 1. And then it anti-commutes with the first of these guys and commutes with the rest of these guys. But there are multiple choices. It's not just one choice. There is a big gauge freedom here. And then this is a formula which lies at the heart of the whole construction. And I cannot stress enough that this is something like a magic formula to me. By magic, I mean that it works. It's definitely correct, and I don't know why it works. And it's much nicer than what it looks. It looks nice in the sense that it is short, but it's miraculous that this formula works. And it's a question maybe also to the audience. I mean, can you connect this formula to earlier things from algebraic beta ansatz? So already this T is something like a double row monodromy matrix. Actually, in some sense, you can simplify it. So there is a certain way of putting this combination into a double row monodromy matrix where you act with this edge operator at the boundary. It's actually not a transfer matrix, but then it will be something like this monodromy matrix element of double row monodromy matrix element. But still, I cannot make the connection to earlier results from algebraic beta ansatz.
So it's this UL, so they are not the zero of the T. So
transfer matrix is not zero, but it's not invertible.
Not invertible, okay. Yeah. But the product is 0. Okay.
So this is this is 0.
It would be 0 because if P.
Yeah. The product is 0, but then you add something in between, and then this is not 0 anymore. And it will work in the sense that if you delete this one, then it's 0. So this means that if you expand this into some power series in UL and you look what happens, then there will be some kind of disturbance originating from this, which spread into the bulk. It's similar to a boundary mode, if you want.
Just a point. If you say, okay, this is matrix formula, but you can say, okay, let's find the states. There exist some states, and you will have product of two eigenvalues, so the UL are the zero of the eigenvalue, but not of the full transfer matrix.
I don't understand. Sorry, what?
My point, because we look at some similar equations, so projective relation, and we can't find the zero of the t using that. And I was with the zero of the eigenvalue. If you imagine you have two functions that should be equal to zero, so you don't have this possibility to have a product of two matrices that gives zero. So if you are acting with their transfer matrix, so you can imagine you have a state. There exist some states. You act and give but you can act with the full formula. So you will find that the eigenvalue, so it's the zero of some eigenvalue, this UL. It's true? Do you think you have some sense of that?
I don't know. I mean, maybe I don't know. But one comment what I want to add at this point is that this looks maybe a little bit strange or surprising. It definitely looks surprising to me. But there is a way to specify this Hamiltonian such that it becomes Jordan-Wigner solvable. It's not obvious, but so these are some coupling constants, and if you set every third coupling constant to 0, which means that you put, let's say, 3L to 0, I mean, this is just a choice. You kill every third term in the Hamiltonian, then that model is actually Jordan-Wigner solvable. It is the same class as the Ising model. So algebraically, it is the same class as the Ising model, and eigenvalues are also the same. It's just a different representation of quantum Ising chain. And then you look again at this formula, and then boom, you recognize that this is the Jordan-Wigner fermions, or creation annihilation created from the chi's. It's not obvious. So we needed to do this computation, but then we convinced ourselves that this goes back to Jordan-Wigner. So this means that this construction is somehow like a parent construction. It works for a bigger class of models, but when we go specifically back to Jordan-Wigner solvable models with Majorana fermions, then we go back to things what we know. So it's not different, it's just bigger. It's a generalization. And then Paul Fendley actually proved that these guys, if you add some normalization factor here, then these guys satisfy this algebra, and then they diagonalize the Hamiltonian like this. And one of the big questions is, why does the whole thing work? And you look at the paper of, yeah?
So what's the boundary condition of the psi? So usually the local operator, if you impose the periodic boundary condition. So after your, for example, for XYZ models, so use the Jordan-Wigner transformation. If you do periodic boundary condition, change to some boundary condition, a twist. So how about the?
So here everything exists with open boundary conditions. I was a little bit, I mentioned it, but I was too quick and implicit. So actually, so this is not completely correct. If the length of the spin chain is L, then here I should write L minus 2. I apologize. And then it goes with open boundary conditions. So it doesn't go around the circle. And there is no way to make, at least as far as we know today, this model is not free fermionic when you put it with periodic boundary conditions. It's really strange, because we know that for normal X6 spin chain, etc., you put periodic boundary conditions, and it splits into two sectors, even and odd, and it's free fermionic in each of them. But here it's different. We don't know what's going on. So the exponential degeneracy is split immediately. It's still integrable, so this we can prove. Actually, Paul proved it, but we also have some additions to it. So it's integrable. Charges exist, but free fermions are destroyed. So free fermion, yeah?
And you don't have translation operator, right?
No, we don't have. And somehow the idea is, this is how we like to see it, that really these free fermionic operators, they are some kind of boundary modes. So you can view it that there is some kind of edge operator, which is somehow a seed of disturbances. And when you work out this expression and you expand it, so you expand different terms here, you multiply them together and see what cancels and what remains, that it will be some kind of, how to say, disturbances which we propagate from the boundary to the back of the chain, such that when you construct operators which spread from here to some certain part, it will be more and more complicated with more complicated coefficients. but altogether the weight of the operators will be homogeneous. What do I mean by that? That even if I show formulas, it is too complicated to understand in one sentence or something. But if you look at normal Jordan-Wigner strings, then you know Jordan-Wigner transformation tells you that you start from the boundary and then you add Z operators, and at the end something happens like X or Y. This is Jordan-Wigner transformation. And then the weight of this operator is still 1. And here we can also show that there are more and more operators. Here there will be actually more and more operators when you move away from the boundary to the bulk of the chain. But the combined weight of these operators will be still homogeneous. I don't know if this is clear, but and this is also unpublished. This we will put into to the next publication. So it's definitely more complicated. My message is that this should be viewed as a boundary mode, where operators originate from this edge mode and edge operator, and they spread into the bulk. That's my point. And this is the reason why somehow it's not compatible with periodic boundary conditions, at least as far as we know today. And in the time remaining, which is not so much, but it's perfectly fine, I want to tell you about our latest results, because this is what I told so far. This was in the original paper of Paul. And this paper focuses only on this model. There is a different representation of the algebra specified by these terms. I will not go into that. And afterwards came 2 papers, different papers. So there was one generalization by Rodrigo Pimenta, who is an organizer but not here, and Francisco Alcaraz, when they looked at certain generalizations of this and parafermionic generalizations or even multi-spin generalizations. And then a different line of thought was done by Stephen Flamia, Adrian Chapman, and collaborators, 2 more collaborators, when they looked at certain extensions of this model, which are also free fermionic when you allow adding more and more terms. And then they have graph theoretical criteria for when can this whole thing work. So it's not necessary conditions, but sufficient conditions. So right now we don't know what is the class of models, what is the full class of models where these formulas work, but there are some necessary, sufficient conditions where we know it can work. And in these papers they actually found 2-dimensional examples also. Very exotic, but in 2D, which is still remarkable, I think. It is published. And then finally, okay, what was in our last paper, what we had? Where did I put the... Here? Or maybe another back? Huh? I'm behind. Yeah, that's fine, that's fine. So for the first time, we actually did something what I would say is also practical from a physical point of view with these models. So we wanted to find correlation functions. Because as you know, in normal Jordan-Wigner solvable cases, there are a lot of things that you can compute with Jordan-Wigner fermions. So not just the spectrum. Spectrum is one thing, very nice, the spectrum or thermodynamics. But maybe you want to do 2-point functions at equal time or different times. Or maybe you want to do real-time evolution starting from some initial state and compute some properties. Because free fermions are nice because you can compute many, many things with your free fermions and give exact results as final results for some quantity. Maybe it can be checked by experiment. Maybe it can be compared to approximate methods like hydrodynamics or something, generalized hydrodynamics, etc. So the big question remained before these work, after these works, what I told about, big question remained, can we do anything practical with these free fermions? And this is what we did in our last paper. We actually computed correlation functions. So it's a big family of correlation functions that we can do. We cannot do all correlation functions, but we managed to find a subset of correlation functions. And I will tell you one example. So let's say we have H1, which is Hamiltonian density, the first Hamiltonian density. So it will be, it's a local operator, Hamiltonian density at the beginning of the chain. So Z1, Z2, and X3. It's a 3-site operator, but it's perfectly fine. And then what we computed is H1 at time 0, H1 at time t. This is real-time evolution, Heisenberg picture real-time evolution. And then correlation function should be evaluated at infinite temperature average. So infinite temperature average is simply the trace. if you want, or no normalized trace. And we computed this correlation function, and we have an explicit formula for this. It looks in the following way. It looks like a free fermionic computation. So it looks the following way. I have an integral from 0 to p. I have a momentum-like variable. I have something like a weight function, which we call c squared of p. And we have something like e to the I, actually a factor of 2, epsilon of p times t. So if you see a result like this, then you know that you can compute this via free fermionic computation, or it's a one-body result in some sense. Because energy enters here, p is something similar to momentum. I mean, these are some time evolution factors that you would normally get, and this is some kind of overlap function or weight function or something. So this looks like pretty much look like an average or normal free fermionic result. Question is, how could we get it, and why do we get it only for this boundary operator? So the reason is that somehow this construction exists in a certain way that it starts from the boundary. That's what I was trying to explain here, that these operators are somehow originating from the boundary. So it turns out that at the moment we can only compute operators which are at the boundary or close to the boundary. It's completely different from normal Jordan-Wigner. In normal Jordan-Wigner case, we can go to the bulk. Actually, maybe boundary is even more difficult, or the same difficulty. Here we cannot do bulk correlation functions, but we can do correlation functions at the boundary. And this is an exact result. It is so exact that we know what is this function, we know what is this function, and we could actually, in a certain case, so if I choose the homogeneous case, that every coupling is 1, then we also know how to evaluate this integral. It will be a generalized hypergeometric function. Details are not important. The important thing is that we have it. And how did we get it? We got this result by solving the inverse problem. This is also a point I want to explain a little bit. So this is the direct problem, so to say, to find the fermions using the operators what are easy to find, this edge operator and transfer matrix. Now the inverse problem is to express local operators using the fermions. And we solve this inverse problem. The first step is that we expressed this edge operator xc0 as a linear combination of the fermions. So we figured out this formula, something like this, where we computed what are these coefficients, what are expansion coefficients. So we proved that the edge operator is actually linear in the free fermionic operators, and we computed these coefficients. And this is what we call the inverse problem, because we use this interacting, we use these many-body free fermionic operators and express the edge operator like this. And then using the edge operator, we can actually find what is this H1 using the free fermions, and it will turn out that H1 will be bilinear in the true free fermions. So it will be a summation with some coefficient of this type. And here is one more thing what I can explain. So at the beginning I said that the Hamiltonian is such that it is not bilinear in the free fermions. Nevertheless, we found that the first Hamiltonian density is bilinear in the free fermions. This is what we found. And we can go also later. So it turns out that for H2, we don't have a formula like this. So we cannot express every term in the Hamiltonian as bilinear in the true fermions, but we could express the first one. This is a strange property of these models. And then later, there are certain types of combinations of Hamiltonian density terms, which will be again bilinear in the free fermions. So very strangely, we found that H2 plus H3, this combination is again bilinear in the fermions. And then later I can find more and more complicated, where actually I need to take products of H's, which are bilinears in the fermions. And if I have an expansion like this, that certain operator is, let's say, linear or bilinear in the fermions, then I can compute correlation functions easily, because in Heisenberg time evolution of operators, I know what happens with the fermions, because they just get a phase. That's where I use that it's free. And once I can add the phases to time evolution of an operator like this, then I can compute some such object, and I can compute this. And to close it, what is the, so to say, physics, if you want. So eventually these formulas are really nice. You can get numbers out of it. It's a many-body problem, because the Hamiltonian is truly many-body. It looks interacting. Free fermions are hidden. it doesn't have U1 symmetry, so it's definitely a many-body problem which is difficult, or at least it looks difficult at the beginning. At the end, we can get numbers out of it, like from this. And we also looked at the t times infinity limit. So we set the length to infinity, so half-infinite chain, boundary correlation function at half-infinite chain, and later we look at asymptotics for large t. And then really strangely, what happens that this decays as 1 over t to the power of 13 over 6. So we found really strange scaling. And this we found first using a computer algebra program, and afterwards we also proved it. So we have an absolutely, well, not absolutely, maybe not for mathematicians, but for physicists, rigorous proof of this scaling. And we can also play around with it. So if we add some staggering to these parameters, then it can change. So if we in some cases it can go back to 1 over t. In some cases it can go to 1 over t. No, actually that's not possible. T to the 3 t cube, or 3 halves. But in the completely homogeneous case, which is a multi-critical point, it behaves like this. And strangely, it is also related to KPZ type of scaling. I don't have time to explain, but it looks that in the homogeneous case, the bulk of this model has KPZ scaling exponent 3 over 2. And then this strange exponent here comes from 2 different contributions which combine, and eventually it will be something strange at the boundary. But somehow this is related to KPZ, at least on the level of scaling exponents. I'm not saying that the physics is KPZ because we don't know. Maybe it's completely different. But the scaling exponents somehow combine. So a normal scaling exponent combines with this KPZ scaling exponent. And eventually, at the end result is this strange thing. Yeah, I mean, that's the end. And we also did some other things, but there is no time to explain. So there is an alternative interpretation of this correlation function where it becomes a fidelity Loschmidt amplitude in a certain quantum quench problem. We also look at quantum circuits. So we claim that we can construct unitary quantum circuits in a quantum computer, and then this process will be classically simulable. And for quantum information, this is important. So we extended the family of classically simulable quantum processes using these hidden free fermions. But that's a different topic. There's no time to go there. And I will finish open questions. So open questions is, what is the family of correlation functions that we can compute in this model? What is the family of correlation functions that we can compute in other models which belong to this family? I didn't put what is the other bigger family, but this is in the works of these the group from the USA. And well, the biggest question is whether somebody would actually simulate this in a quantum computer. Well, not biggest. Theoretically, it's not the biggest question, but it would be really interesting because we provided all the mathematical details. So we provided the quantum circuit. It's even factorized into gates which exist on quantum computer. So correlation function like this, it could be actually implemented on a quantum computer today, and then it could be checked. So the result of the quantum computation in an actual superconducting or ion trap or some supercomputer could be checked against the analytic result. It would be interesting because it's a new type of benchmarking. So thank you.
So any question?
So question about this inverse problem. So how exactly you know? So because even in normal Jordan-Wigner, it's not a problem if it's like expressed in like many fermions, not just linear. Because okay, you will have some Freedom determinants or whatnot. So it's not like big problem. So if you know exactly, or you don't know, so there's a question. So you know, for instance, like to express Zj through fermions?
No.
Ah, okay.
So somehow, this is the first. So this was the first work what we published. We don't know yet, but we are quite sure that it will be only a subset of operators that we can express. Mm-hmm. But there could be some operators which are expressible, which are very complicated using the psi, but still exact formula can exist. So like something like what you would say, like it involves linear, bilinear, etc., maybe a big series, but still exactly known.
Yeah.
And we don't know yet. But we are quite sure that there will be some operators which are completely outside of the free fermions. And the reason is that the free fermions are fewer than the Hilbert space. It's always fewer. So because we have L over 3 of these free fermions only.
Oh yes, that's absolute mystery, but maybe we should talk.
Yeah.
And another quick question: what prevents you to compute at finite temperature?
No, we can. It's just time limit and yeah. And we can also do ground state. I mean, this was the easiest because trace is easiest, but we can do any. I mean, we plan to do for a longer paper. So now we put a short paper, just publish what we have very quickly, and we will do longer.
Maybe my memory a bit rusty, but I remember already 22 there was discussion how to put it into the quantum inverse scattering method terminology, all this stuff, and there was already Lux operator and R matrix. And as far as I remember, this R matrix was nothing but Per-Schutz model SL/2/1 with special points. So not very clear your statement that it's not clear connection to exact integrability.
Because we never managed to use this observation.
Okay, but the connection is clear. It's just very special point where beta ansatz is collapsing and so on.
Okay, so I forgot. So Arthur is right. I mean, he was member of our group when we discussed this and we discovered, but it's really not clear how to use. So it's a very special degenerate point of some quantum group. And all of this structure doesn't depend on that quantum group at all.
Yeah, but it's a problem of beta ansatz. It's not your problem. That's the way I'm let's say. But it's a connection is clear. It's just beta ansatz in this point very bad.
Yeah.
Other question?
So if I understand correctly, this the power law decay, you could think about the number appearing there as a function of the inhomogeneity of your system. So do you have an understanding like what would be the slowest decay or?
No. Again, the idea was to publish what we have, and we played for 1 week or 2 weeks, and we show numerics was not clear. I mean, we can do analytics only at the homogeneous point, and numerically we saw some other things, but there are some phase transitions or maybe some crossover. We don't even know. So we want to analyze later.
But the kind of minimal result that you have is that actually the staggered decay slower than homogeneous, or did I get it wrong? Because this 13/6 is for homogeneous.
Yes. Yeah. That's a minimal result, but it's not published. So it was what we observed. I think even numerically. So. Yeah.
Okay, thanks.
But so this is a multi-critical point, and then staggered can be just simply critical, or it can be off-critical also. And by critical I mean, so again there are these degeneracies, exponential degeneracies, but let's forget about them and let us just look at the spectrum. So energy is exponential there, but I don't care, and let's look at gaps, and then you can still define if it is critical or off-critical, and then some if it is staggered with no, so if it is staggered with period 3 and nothing coincides, then it's off-critical. If 2 of them coincide, then it is easy universality class. And if it is homogeneous, then it's a multi-critical point. Yeah.
Last question?
So, how you start from the Hamiltonian, then you construct a transfer matrix for the quantum spin chain. Actually, we start from the R matrix. Is standard way to construct the transfer matrix. So, how to start from Hamiltonian to the transfer matrix, because you are transfer of the precise stuff.
Yeah. So okay, I can tell because that's nice, but I didn't want to put to the main part of the talk.
Oh, yes.
So there are 3 definitions of transfer matrix. And I can tell you one definition which uses only the Hamiltonian, okay? So let's say that the Hamiltonian is, I will do here. So let's say the Hamiltonian is the sum of Hj operators, where Hj includes also the coupling and the Pauli string. That's just a choice. And then the transfer matrix is the following. It starts with 1, the identity. Then I add u times the Hamiltonian, And then I add u square maybe over 2 times product of these guys h, j, h, k, where j is smaller than k. And not just this, it's actually smaller than, how is it? So they should commute with each other. So it should be, no, I made a mistake, sorry. So j plus, how is it? Is it correct this way? Let me think. Yes, I think it's correct like this.
Yeah, just give the idea how.
Yeah. So and then I move on. So u, and then I take this h, j, h, k, h, l, a product, order 3 product that everything should commute with each other. So they should be a little bit far away from each other. If they are neighboring, then they anti-commute. Then I don't add it. And then this is called something like, from graph theory, this is known as independence polynomial. So this is operator valued independence polynomial, if you want. And then you move on until it stops. But you can write this big polynomial also as an MPO using Lax operator, but that's more strange. And you can also view it as a double row monodromy matrix. But is maybe even more strange. But so there are different ways. This is and that you can also figure out a recursive definition like this, where the recursion takes into account volume. But again, it's similar.
Okay, so any other question? Give us. You have to go to lunch.
Hi, it's probably a naive question. So you said that this openness is sort of intrinsic.
Yes.
Is there any way to take sort of a limit to the closed case? So in XXO chain, you do the attenuating limit, for example.
Yes, and we played with it, but only numerically. And the idea would be to start from periodic case, and then let's take 2 couplings and then tune them to 0. And we know that if I tune 2 couplings to 0, then this means that I cut the chain and then it's open and free fermionic. But we see that as soon as we put these couplings back, the free fermions get broken. But there are some signs that it was originally free fermionic. So this is physically also interesting, but we didn't publish so far. We haven't published because we don't really know what to do. Because imagine that you have a big system, like I don't know, 100 spins or something. And if it's open, then we know it's free fermionic. But then you close the system, which means you add 2 Hamiltonian terms such that you glue it together. Which means you don't do very stupid things. No, it's just really big system and you close it. So this means that for physical properties, you should still see the free fermions because you just take a perturbation locally. And we see this. So on the entanglement spectrum, we see the origins of these free fermionics and the large degeneracies. So even the periodic system, even though it's not free fermionic strictly, it shows these signs that it was free fermionic, we just did something stupid, but not very big problem. And we don't know. So as soon as we go to periodic, the exponential degeneracies, they split, but they split in a small way. So even when you look at, so for example, we did these plots, it's unpublished, maybe we will publish it soon. You know, some people do these plots that here is energy and here is entanglement. So you diagonalize your spin chain, you cut it into 2 halves on a periodic, but you cut it into 2 halves and you compute what is entanglement between 2 halves. You compute it for every state and then you do a scatter plot. And then if it's a chaotic model, you see something like this. In the middle of the spectrum, high entanglement, here are ground states, small entanglement. Now we see more scattered things, but we also see something like this that so states which are close in energy, which means they originate from the original free fermionic degenerate things, but they split a little bit and then they have different entropy. So we see some strange things which originate from these free fermions, but we don't know what to do with it. Yeah.
Okay, so maybe we can end now. Anyway, so for the lunches, we have to move from the university and there's some small restaurants waiting for us. And probably you can leave things here. I will close the doors before leaving, if you need. And maybe if we meet in 5 minutes, just in front, I will show the way.